This video is an introduction to the polar coordinate system that is an alternative to our usual Cartesian coordinate system that we've been using since primary school. So we're very used to dealing with Cartesian coordinates. We're very used to using the x and the y coordinate to be able to locate a point. For example, the point 3, 4 means I go along 3 squares in the x direction and I go up 4 squares in the y direction. So that defines this point here. But that very same point, I could define that in a different way. I could describe that as being 5 squares directly away from the origin in a straight line with an angle of 0.927 radians from the x-axis. With those two pieces of information, that uniquely defines that point. Because saying that it's 5 squares away from the origin, that means that it could be anywhere on a circle that's 5 squares away from the origin. But by me specifying that angle there of being 0.927, that means it specifically has to be that point and none of these other points. So we have a slightly different way of being able to define a point with a distance away from the origin and an angle that it makes with the x-axis. I got the 5 and the 0.927. I got those because I've got a right angle triangle here where I know that this side here is 3, I know that this side here is 4, and by doing some Pythagoras I know that this is 5. And to get this angle here I can do some trigonometry. I could say that tan theta equals the opposite divided by the adjacent, and then I can do arctan inverse tan of both sides to get the 0.927. So that's where I got those numbers from. So this is our polar coordinate system. Now the key thing here, the two key things I should say, is the distance away from the origin and the angle it makes with the x-axis. So the y-axis, this y-axis here, is not actually very important at all anymore. So we don't actually include it when we're doing polar coordinates. I'm not going to include this line at all. And similarly, I don't actually include the negative part of the x-axis either. In fact, I don't even call it the x-axis anymore because in polar coordinates, we don't have an x-axis. We have a distance away from the origin, which we call r, and we have the angle that's being made, and we call that the line that the angle is made with, we call that the initial line. So let's talk a bit more generally and how we can convert between coordinate systems. So, if I have a coordinate x, y in Cartesian form, and I want to convert that into polar form, into r theta form, to get the r, because I know I've got this right angle triangle here, where this is x and this is y, and this is r. To get the r, I know I can just do a bit of Pythagoras. R squared is equal to x squared plus y squared. To get the angle here, I know I can do some trigonometry. I can say that tan theta is equal to the opposite divided by the adjacent, the y divided by the x. Therefore, the angle would be the inverse tan of y over x. I can also say that cos theta is equal to the adjacent, which is x, divided by the hypotenuse. So x divided by r, which then if I multiply both sides by r, I get x equals r cos theta. And similarly, if I said that the y, that's my opposite, and this is my hypotenuse, so I could also say that sine theta equals the opposite divided by the hypotenuse, so therefore y equals r sine theta. So my point is then, at the bottom here I've summarised these formulae. If I want to convert from Cartesian, from x and y, into polar, r and theta, then I can use these two green formulae to do that. If I wanted to go the other way, if I wanted to convert from polar form, from r theta, and I wanted to go back to our traditional Cartesian form, then I could use this equation here to work out the x coordinate, and I could use this equation here to work out the y coordinate. So let's have a look at a few examples. Let's convert some, actually before we do that, before we look at a couple of examples of this, those are just the formulae. I've not actually talked about why this is useful, why we even do this in the first place. And it's because there are actually a lot of situations where Cartesian coordinates are really, really bad. They're really good when we're looking at x and y coordinates and things that are perpendicular to one another, where things move in directions that are perpendicular to one another. X and y coordinates are great for that. But when we're looking at things like circular motion, how things move in a circle, or how things orbit one another, or how things move around a circle, or in a cylinder, or in a sphere, any of those situations, our Cartesian coordinate system really struggles. It's not impossible, you can do it, but just the maths becomes really, really awkward, because having an x and a y that are perpendicular to one another doesn't deal with circular things very well. You can see this spiral curve that I've got here. The Cartesian equation for that is the square root of x squared plus y squared equals arc cos of x divided by the square root of x squared plus y squared. That's an absolute mess. Really, really awkward. But in polar coordinate form, the polar equation of this spiral is really simple. It's just the r coordinate is equal to the theta coordinate, the angle. That's it. The radius is equal to the angle. And we'll see in the next video about sketching these and why it is that this describes this. But the point I'm trying to make here is that in these situations where we have circular motion, or any situation where we're just trying to describe circular things, Cartesian coordinates are really awkward, and polar coordinates are really, really easy. So I know that you're all really used to using Cartesian coordinates, and you like them, and you're comfortable with them, but in the future you will hopefully be tackling some problems that require much more advanced maths than Cartesian coordinates. And the polar coordinate system will really help with that. So, let's have a look at a few examples excuse me, of converting between them. So I've got some Cartesian coordinates here, and I want to convert them into polar coordinates. So I've got the coordinate 5 minus 12. So the x coordinate is 5, the y coordinate is minus 12. So to find the r here, I'm going to say r squared equals 5 squared plus minus 12 squared. So r squared is going to be 169. So r is going to be plus 13. R will always be positive. You're never going to have a negative radius with polar coordinates. Next, we need to find the theta, the angle that's being made with the x-axis. To get that, I'm going to do theta equals arctan of minus 12 over 5, excuse me, which, when I type that into my calculator, I will get minus 1.176 radians. So this, if I was to draw this out then, just to help you visualize, that's the coordinate in polar form. 5 minus 12. What I'm saying here is this coordinate here is exactly the same as this coordinate here. Just one's in Cartesian form, one's in polar form. Just to help you visualize, let's draw that out. So in Cartesian form, the 5 minus 12 is down here. In polar form, what we're saying then is this length there is 13. We're saying that this angle is 1.176. The reason why it's negative is because it's below the x-axis. Alternatively, you could give it as this angle, which would obviously be 2 pi minus the 1.176, which is 5.107. So you could also have given your answer like that. Either way is absolutely fine. Next example, we've got the Cartesian coordinate minus root 3 minus 1. So first of all, let's get our r. So r squared is equal to minus root 3 squared plus minus 1 squared. So r squared is 4, so r is 2. Let's get the angle now. So theta equals arctan of minus 1 over minus root 3, which if I do that, I get pi over 6. Now I have to be careful with this, because that pi over 6 is not actually correct. The reason why that's not correct might not become clear unless I draw a diagram. So with these, I would always draw a little sketch just to help me visualize. The minus root 3 minus 1 coordinate is actually down here. Excuse me. Where, yeah, so this is the minus root 3, that's the minus 1. We've just found that this is 2, and we've just found as well that this angle here was pi over 6. So in terms of the angle that I want, this angle here, I'm going to have to do pi plus pi over 6, which is 7 pi over 6. So the answer I need to give here would be 2, 7 pi over 6. Alternatively, I could give it as 2 and minus 5 pi over 6, because this angle here would be 5 pi over 6. And that's below the x-axis, below the initial line, hence why it'd be minus. So you could give this as your answer, or you could give this, but you certainly can't give that. That is definitely wrong. So a sketch is really important here. Don't just use the formulae. Use the sketch so you can visualize what's going on. Right, what about going the other way? So we want to convert these polar coordinates into Cartesian form. So we're using these formulae to help us do this. Because we're trying to turn the r and the theta into an x and a y. So the x coordinate I know is r times cos theta, which if I type that into my calculator, I get minus 5. And the y coordinate is going to be r times sine theta, which gives minus 5 root 3. So in Cartesian form then, this coordinate is minus 5 root 3. Next one, same idea, x equals r cos theta, which is minus 4. Y equals r sine theta, which is 4 root 3. So this coordinate would be minus 4 root 3. And there we go. So that's converting coordinates both ways. Now let's look at how we can convert equations both ways. So the first one here, I want to convert the polar coordinate, the polar equation r equals 5 into Cartesian form. Now, r equals 5, that's saying that the radius, the distance away from the origin, is always 5. The distance away from here is always 5. So 5, 5, 5, 5, 5, 5. The distance away from that point is always 5. So this is a circle. Centre is on the origin. The radius is 5. So straight away you might be thinking, well, I know that's going to be x squared plus y squared is equal to 25. Alternatively, we could do that a slightly different way. If I square both sides, I could say that r squared is equal to 25. And from our rule here, we know that r squared is equal to x squared plus y squared. So there we go. I have turned the polar coordinate r equals 5, polar equation r equals 5, into the Cartesian equation x squared plus y squared equals 25. Like I was saying earlier, you can see why polar coordinates are much easier. R equals 5 is a much easier equation to use, much simpler than saying x squared plus y squared equals 25. Right, next. R equals 2 plus cos 2 theta. So I want to turn this into Cartesian form. Now, in order for me to get this in terms of x and y, I want to try and use these formulae down here in the bottom right. I want to try and use that x equals r cos theta, y equals r sine theta. I'd like to try and use these somehow, along with the r squared equals x squared plus y squared if I need to. But my point is, at the moment, I need to do something with this too. Now, I know that cos 2 theta is the same thing as 2 cos squared theta minus 1. This is just double angle formulae from regular A-level maths. So I can then simplify this. The 2 minus the 1 is like that. So I've got a cos squared here now, which is getting close to me being able to use this x equals r cos theta. I would like it if I could have an r squared in front there. So I have an r squared cos squared. That way I could turn that into an x squared. Imagine down here if I could say x squared equals r squared cos squared. So the only way I could get an r squared there is if I multiplied both sides by r squared. So that would give me r cubed equals r squared plus 2r squared cos squared, which now I can change a few things here. I could replace the r squared with a x squared plus y squared. The 2r squared cos squared, so r squared cos squared, I can replace that with an x squared. This is the same thing as x squared from here. And now I'm just left with the r cubed. Well, I know that r would be this, if it was just r, that would be the same thing as x squared plus y squared all square rooted. But this is r cubed, so I'm going to cube that. So it would be at the power 3 over 2 now. And now I've got this only in terms of x and y. This is a Cartesian form now, which is good. All I want to do now is collect up those x squared and the 2x squared terms, like that. So there we go. This is the Cartesian form of this. Again, I would argue quite clearly this is much simpler than this awkward thing. But you still need to be able to convert between the two of them. Right, last one. R squared equals sine 2 theta. Again, like the previous example, I want to try and use these formulae to help me to do this, so I don't want that 2 there. So I'm going to use the double angle formula to expand this. I'm going to say r squared is equal to 2 sine theta cos theta. Also, like before, I would like this to be an r sine theta, so I could replace it with y, and I would like this to be r cos theta, so I could replace it with x. The only way I can introduce those two r's on the right hand side is if I've multiplied it by r squared. So I'd have to do the same thing on the left hand side. So I'm just timesing both sides by r squared here, which is going to give me r to the power 4 is equal to 2r sine theta r cos theta. Now I have what I want here, that's y. This is x. And this, the r to the power 4, that's r squared squared. So I could replace that. That's my r squared squared. So that's my r to the power 4 equals 2 times y times x. And there we go. We have it in Cartesian form. This is the Cartesian version of this. So that's how we can go one way. That's how we can convert polar coordinates into Cartesian form. What about if we're going the other way? What about if we want to convert Cartesian into polar? So I've got the equation y squared equals 4x. I know that y is equal to r sine theta. So I can replace y squared with r sine theta squared. I know that x is equal to r cos theta. If I expand out the left-hand side here, I'll get r sine squared theta equals 4r cos theta. And all I want to do now is to rearrange this to make it so that r is the subject. In the same way as with Cartesian, we're always writing y equals a function of x. I'd like to be able to say that r is a function of theta. So I want to make r the subject. So if I divide both sides by r, which I'm allowed to do because r will not equal 0, I'll get that. Now I'm going to divide both sides by sine squared. So r equals 4 cos theta over sine squared, which I'm going to write as sine theta times sine theta, because that will allow me to simplify this to be 4 cot theta. That is the cos theta over sine theta. And then I've got the 1 over sine theta, which is cosec theta. So this is the polar form of this. Next, x squared minus y squared equals 5. Again, let's substitute the r cos theta in instead of the x. Let's substitute the r sine theta in instead of the y. And let's expand those brackets. To give that. I'm then going to factorise the r squared outside. And this is where it is very, very useful if you are good with your trigonometric identities, which you really need to be for further maths. You need to be that for regular maths, but especially for further maths. Cos squared minus sine squared, you should be able to straight away think, right, that's the same thing as cos 2 theta. That's your cos double angle right there. We can then divide both sides by cos 2 theta, which is the same thing as r squared equals 5 sec 2 theta. There we go. Last example now. First step, exactly the same. Let's replace that y with an r sine theta. Let's replace that x with an r cos theta. Like that. I am then going to collect up the r terms. Remember, I'm trying to make r the subject here. So let's subtract that r cos theta away from both sides. So I've got r root 3 sine theta minus r cos theta equals 4, and factorise the r outside. At this stage, we would like to be able to do something with this like we did with this. We'd like to be able to group those terms up if we can. But there is it's pretty tricky to be able to see how to do that. Like I was saying before, you guys need to be really good at your trigonometric identities now. So we've got a sine theta minus a cos theta. So I'm thinking about the addition formulae. And I'm thinking about the sine of theta minus something. Because I know that gives a sine theta cos something minus cos theta sine something. So now I'm looking at these angles, or sorry, not these angles, these coefficients. I'm looking at the roots 3 and I'm looking at the 1 that's in front of the cos. And then I'm also thinking about the exact values of trigonometric functions that I know. So this is why I'm now thinking I'm going to divide both sides of this by 2. The reason why I'm doing that is root 3 over 2. That is an exact trigonometric value. And 1/2, that is an exact trigonometric value. And remember what I was saying about in order for me to use the sine of theta minus something, remember that gives me sine theta cos something minus cos theta sine something. So what angle is it now that when I do cos, I get root 3 over 2, and when I do sine to the same angle, I get 1/2. It's pi over 6. Cos pi over 6 is root 3 over 2, and sine pi over 6 is 1/2. So I'm going to rewrite this form, so that I can then factorise this using the addition formulae as sine theta minus pi over 6 equals 2. I can then divide both sides by the sine function, so r equals 2 divided by that sine function, which would be the same thing as cosec. And there we go. That is the polar form of that equation. So just to summarise them, those formulae at the bottom there, the r squared equals x squared plus y squared, the theta equals arc tan y over x, the x equals r cos theta, and the y equals r sine theta, allow you to convert between Cartesian equations and polar equations. You need to be familiar and comfortable with equally comfortable working in both systems. I'm not saying that one is always going to be better than the other. It depends on the situation. You're going to need to be the judge of what that situation is and be fluent working in both coordinate systems. So this has just been an introduction to what polar coordinates are, why they're useful, and how we can convert between them. We will be doing more work on this over the next few weeks so that you become more fluent in them.